Okay, so this represents the transmutation that I was showing yesterday. And how many half-lives did we get through yesterday?
One.
Just one? All right, and I didn't have enough up here. Okay. All right, so we started here, so
You still need one more.
I think recently I just need a couple periods to get me all fired up about the day. 'Cause I seem to do better in the afternoons recently. You guys are seeing all my mistakes. All right. Or maybe it's just this class. Mass, time, half-life. This chart is how you're going to do all these practice problems today. And mass means the isotope that is decaying, not the one it's turning into, even though I do put that in my first example here. So here's the AR's mass. This is going to be the K. So initially we say, okay, nothing has happened, right? So like the stopwatch I said, we haven't started timing. We hit the stopwatch. All right, now what did I say we started with? 16, right? Each one's a gram. So 16 grams of that, 0 grams of this. So I want you to fill in your chart. Okay, humor me today for the first couple examples. Do it exactly as I do it up here. On your homework, do whatever you need to do to show work and get the answers. If you understand how to do this and you want to do it a little differently and show work differently, I'm fine with it. But initially, just do what I'm doing. All right, so time is 0, half-life 0, meaning you have all of the particles. They have not decayed. They have not given off radiation yet. All right, after one half-life, what is the half-life of this thing again? 1.23 seconds. Half of these particles, and it's random, half of these particles will decay. So I will have 8 grams of K and 8 grams of argon. Because K is turning into argon as it gives off radiation. That's transmutation. It's natural transmutation, but it's transmutation. So again, 8 of these will randomly turn into argon if argon's yellow. All right, so if I just take 8 of these randomly away here. And we'll take these two. And we'll take this one. We'll take the middle there. What's that? 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So now that's what the substance looks like after one half-life. So mass doesn't disappear. So 8 grams doesn't just like vanish. So if this was actually like sitting on the table, like those discs in the back, it doesn't start to shrink. It's not actually losing mass. It's just being converted into something else that is within the same exact sample. Right? So if this was the potassium, you wouldn't be able to know it. You'd know it by looking at it, but half of these atoms would now be turning into argon. All right? And it would so it's not disappearing, right? It's transmutating into something new. Well, not technically. I lost it. Most of the time on the regions, they're not asking about this. They're always asking about the original. How does this one change? This is more of an advanced concept, actually. But anyways, after 1, we're down to 8 grams. So now, after 2 half-lives, how much time has passed? 2.46 seconds, right? 2.46 seconds. And 4 grams remain. And how many grams of argon do we have now? 12, right? Because 4 of these, 1, 2, 3, 4, have turned into argon. 1, 2, 3, and one more. Okay, so as you can see, the mass of K is decreasing by half every time, but the mass of argon is increasing. Okay? So eventually, all these reds are going to turn into yellow. Again, one more half-life. How much time has passed? 3.69 seconds. 2 grams of potassium remain. Why? Because an additional 2, half of 4, has decomposed, or decayed, not decomposed. Decomposed is a chemical term, not nuclear. Decay. All right, and now we have 14 grams of argon. And then we go one more. How much time has passed? 4.92. Yep, 4.92 seconds, we have 1 gram and 15. And then it's a coin flip, another 1.23 seconds pass. This may or may not change. Every single half-life, it's like it's a coin flip, heads or tails, like a lab. It's a probability thing. So it might not actually turn, but eventually it probably will, okay? Especially if it's a very short half-life. So what are we trying to understand here? One, how to solve half-life problems. If I was to say, all right, you have 16 grams of potassium and 4.92 seconds pass, how many grams remain? This is one way of solving it. You set up this chart and you fill it in. I know it's tedious, but it really helps us understand all the parts. How this decreases, how time increases by the same amount every time. The half-life never changes. It's always 1.23. And then this just keeps track. Once you get good at this, this becomes tedious for some kids. They don't want to do it because they know how to do it. So they just do the math, they show the work, a little bit of work, and they get their answer. I'm fine with that on the homework, but right now I just want you to do it this way at least one more time in the notes. So we're learning how to set up the chart, solve problems like the one I just had with carbon-14, but also understand like the concept and visualize what's happening when something's decaying. The magnets is the best way I can show it. All right? So eventually, all radioactive substances will not be radioactive anymore, and they will have turned into something else. So once all the K turned into argon, it's not radioactive anymore. Well, actually it might be. I don't know if that is or not. But usually these are more stable than what they started with. That's the whole point of radiation, radioactivity. All right, so that's half-life. Questions? Is it making sense to us, most of us? Hopefully all of us. Did your brother tell you the joke from yesterday? I said to Tyler, Tyler, why is... I'm so limited sometimes in my brain. I have to do a very simple joke. Why is 6 scared of 7?
7, 8, 9.
Hey, man.
I was about to say that.
You took my punchline. Your brothers had never heard that before.
What?
I was like, tell your sister if she hasn't
No
either.
way. That's like the most common
Seven.
joke like
That's
ever.
like
Who has not heard that?
Be honest, like actually, has everyone heard it?
Wait. Did I tell you the 2 atoms walking down the street joke?
I don't think so.
2 atoms walk down the street. One turns to the other one and says, hey, I think I lost my electron back there. The atom goes, are you sure? The atom says, yeah, I'm positive. Because if you lose an electron, you're positive. And then the ones at the bar, proton, neutron walk into a bar. Proton orders a drink, bartender charges them whatever, $5. Neutron says, I'll have the same thing. Bartender says, for you, no charge.
Huh, because no charge, it's the
Neutrons have
neutron.
no charge.
That was stupid.
Why did not You're gonna tell your daughter this joke, she's gonna be like, shut up.
He probably looks him up by
I would tell you another chemistry joke, but they're argon. Argon. They're
That's
argon.
so stupid.
They're bad.
Do you like actually look up chemistry jokes on your
It's like
own?
chemistryjokes.com.
For years, there was always kids who were they just like you guys. You're like, oh my god, this guy's a fool. But the kids would look up chemistry jokes and write them on the board or tell me, so I just remember them over time. No, I don't look them up. Some I just I don't look them
Just like
up.
with that
It's like
tinfoil
a
guy, he
baby
said he
for
doesn't
these
have.
kids, you should sit there like, okay, cool, bye.
What are we talking about, my daughter?
Yeah. Dude, you're gonna get older when you actually start understanding it. You just like, can you just get out of my room, Dad? Like,
She'd be like, why aren't you cool?
We'll see. All right. Now, before I'm glad I wrote my note here because I forgot yesterday. Before we do more half-life problems, I want to talk about pros and cons of nuclear power because that is something that could be on the Regents, and it's good to just have general life knowledge here. So let's just talk about it. Nuclear power plants. Okay. Would you want to live right next door to one?
No.
Why? Okay. So that's a negative, I would assume. Negative. So con, right? Negative is radioactive waste, radiation. That could leak into the environment, okay? And this isn't anything we necessarily need to write down. You can if you want, you're worried about remembering, but what else? What other negatives might there be about nuclear power plants? That's the most common one, by the way, is it produces radiation. The waste we have to do, right. So there's radiation that could leak into the environment, and we also have to store the radioactive waste. That's kind of the same, but also a little different. Yep, because the waste can stay radioactive for like hundreds of years or thousands. Which means, like, you know, if you get a job at a nuclear power plant, let's say you're young, 21, 22, and let's say you work there for 50 years, well, eventually you're gonna die, and that stuff's still radioactive, right? So it's like other people have to, you know, have a good record keeping. What else? What other negatives or positives? Either one.
Could blow up.
Okay, it could melt down. That's a problem. And release radiation into the environment.
Give us electricity.
Yeah, that's a positive. It produces electricity and it's really efficient. 2 pounds of uranium, 40 million pounds of dynamite. 2 pounds of uranium. That's not that much for all that energy. It's very efficient. It's a lot of electricity. What else? Look at your fission reactions in your notes. What's not a product that is a huge problem with the planet right now? What's not a product that is a big problem of what we constantly spew into the air? There's no CO2, there's no methane, there's no greenhouse gases, there's no pollution. I don't know if you guys realize this, but the word pollution technically only means gases put into the atmosphere. That's what pollution means. If you were to, you know, I don't know why in the world you would do this, but driving down the road, throw a can out the window, that's not pollution, that's littering, that's garbage, but that's not called pollution. Pollution is technically air, like air pollution. So yeah, there's no pollution with nuclear power. Okay? No greenhouse gas. It doesn't affect the climate change. It wouldn't. We have to store radioactive waste. So no pollution, lots of electricity. Those are two big positives. Radiation leaking in the environment, that's a negative. You think it's cheap to run these things? No, really expensive. Nuclear power plants can only exist about 10 years maybe, then they have to be dismantled. You know, whenever I record myself, I always get nervous. Like, I say things sometimes, I'm not 100% sure, so I have to tell you that. I'm not 100% sure on that 10-year number, but nuclear power plants can't exist forever. They become there's too much radiation in the building. They have to dismantle it. So that's expensive. One more thing, positive. I need someone to work there. Jobs. All right, that's a positive. So just keep those things in mind. A lot of that, I hate to say common sense, but it kind of is if you think about it, right? It produces electricity, that's a good thing. There's radiation, that's a bad thing. All right. So something I forgot to talk about yesterday with you guys. All right. Let's put the carbon-14 problem in our notes now, and then we'll do another one, and we'll see if we have time for 3. We'll see. All right. So I'm just going to reword it. How many grams of a 100 gram sample of C14 remains after 17,145 years pass? So get that in your notes so you have something to look at if you get confused later today or tonight whenever you do the worksheet. All right, the answer is 12.5 grams. But I'm going to set up the chart, show you how to solve it, and then we'll hopefully maybe squeeze in 2 more examples here. Different ways to ask half-life questions.
Oh, the wind's whipping out there.
Yeah, it's been really windy yesterday, last night, today. All right, so here's how we do this. I always tell kids, especially students who are kind of confused with this and they don't know how to do these very well. Always set up, oops, not years, what am I doing? Always set up your chart. Mass, time, half-life. Those are your headings. Your time and your half-life are always 0. Always. Meaning time hasn't started yet. So initially, you have all 100 grams of carbon-14. And now the way Reagan did it, and I think Zeke nodded, and Nicole, I think, nodded too. And some others did too. But the way Reagan did it is a good way to do it. She said, let's take 17,145 and divide it by 5,715, and we get 3. So if you take the total time and divide it by the half-life, it tells you how many half-lives it goes through. So you don't really need to fill in this time. I'm going to do it just to show you the slow way of doing it, because I think for some kids that helps. But you really don't need the time. You just have to say, all right, 1, 2, 3. I know it's gone through 1, 2, 3, so I know this 100 splits in half 3 times. So that would be 50, that would be 25, and that would be 12.5, and that's my final answer. But the other way to do it, if you don't get this here, this quick math, or you don't like it, or it's confusing, for whatever reason you don't like doing this, you can just fill in your chart one half life at a time until you get to that number. Then you stop. So in other words, you would put this here, that is the half-life from table N. Then you would add the half-life again, because the half-life is always the same. That never changes. So that would be 11,330, 11,430.
You're right.
Yeah.
Yep. And then add it again, you would get 7,145. So again, if you're confused with this, you can just keep adding the half-life until you reach the time the question's asking about, and then that's your answer. As long as you split this in half every time. Alright, so that's just one example of a half-life problem. I'll do another one that's a little bit different. Questions before I move on? Okay? So now, sometimes they ask the question in reverse. So it says, if 1 gram of, I'll pick an isotope here, let's go with K42, remains unchanged after, I'm just going to make these up on the fly here. 49.44 hours. How many grams were in the original sample? So this is same type of problem, just asked in reverse.
Does that mean we're gonna have to go up?
Right. So in the chart, we're going up. So you still have to figure out how many half-lives it goes through, but you're working backwards. So you start with 1 at the bottom, and then go up to whatever the starting mass is. So I'll give you like a minute to think about it, and then I'll go through it because the bell's going to ring in like 3 minutes. So I know this goes through 4 half-lives. 1, because I made the problem up. But 2, the half-life of K42 is 12.36 hours. That's on table N. If 44.9 or 49.44 hours have passed, we divide that by the half-life, we get 4. So I know it's gone through 4 half-lives. So down here, eyes up here, right here, this is 1 gram. That's what the question told me. After 49.44 hours have passed, it tells me I have 1 gram. We got to go all the way up to the question mark. So if we're working backwards, we don't cut this in half. What do? We double. Half-life is the mass cut in half. Well, if we're going the other direction, then you have to double everything. So this is 2, 4, 0.8, 16 grams is the answer to this question. So it's exact same concept as that first question, except we're going up the chart. So if going down the chart you cut in half, going up the chart you double. So the answer is 16 grams. Because the half-life here is 12.36. We don't need to fill that in because we already figured out 4 half-lives. Questions? So the homework is practicing more of this. There's a couple other types of problems I didn't go over yet, didn't have time. But you have the general idea, so take what you learned, apply it, see what you can do. All right, we'll go over it tomorrow. And that's it.